All right, AEW number 13. We're actually getting close to the end of the semester. So we're starting with some review, the derivatives. So with A, you could start by just doing the quotient rule. So start by taking the derivative of the top, and derivative of x plus 4 is just going to be a 1. And then leave the square root of x alone. Minus, now leave x plus 4 alone. And then take the derivative of the denominator, which is 1 over 2 times the square root of x. And then the last part of the quotient rule is you just square the denominator. And then we're going to need to simplify. Well, for one thing, the bottom is going to be easy to simplify because the square root and the square cancel and it just leaves x. And then for the numerator, I need to get rid of this little complex fraction that was caused by the 2 square root of x. So I'll need to multiply on the top by that and on the bottom by that. So on the top, when you distribute it, the 2 square root of x times another square root of x, that's just going to be 2x. And then when you distribute it to this one, they're actually going to cancel. That was the whole idea of that. And then on the top, just distribute the negative. So it's going to be negative x and negative 4. And then that simplifies a lot because 2x minus x will just be x minus 4 over x. And there we go, there's number 1, part A. I was also thinking there's another way to do part A. And that is you start over, and at the beginning you do algebra. And just separate this into 2 fractions, as long as you keep the common denominator, the square root of x. And then the first numerator will just be x, and the second one will be plus 4. And then still do algebra, so simplify the first one. So if you subtract the exponents, this one would be a 1, and then this one would be a half. So 1 minus a half is a half. Or in other words, that's square root of x. And then I could rewrite this one as 4, and then x to the negative 1/2. And then take the derivative. So the derivative for square root of x is going to be 1 over 2 times the square root of x. And for the second one, use the power rule. So take the negative 1/2 and multiply, and then subtract 1 from the exponent. So what does that leave? Negative 1/2 times 4, so that's a negative 2. And then x to the negative 3/2. Or if you don't leave any negative exponents, this second one is going to be negative 2 over, well, let's see, this means square root of x cubed. So for that one, the work was a little bit easier, but the answer is more complicated. Jose, what was the answer I got the first time? Wasn't it just x minus 4 over x?
It was x minus 4 over x, yeah.
Yeah. Are those the same? I'm just curious. Let me see if I multiply by a square root of x on the top and the bottom, and I multiply by the square root of x on the top and the bottom, then this one equals square root of x over 2x for the first fraction minus 2 square root of x. And then this one has an exponent of 1 and this one has an exponent of 3. So that means you add them together, it's an exponent of 4. And the square root of that means it's going to be x squared. I don't know, is that the same answer? All right, get a common denominator. So this one I have to multiply by x on the top and the bottom. And this one I have to multiply by 2 on the top and the bottom. So that equals, let's see, a common denominator of 2x squared. And then an x times square root of x is x to the 3 halves minus 4 square root of x. Well, I think that it's going to be the same because it has that extra 2 on the bottom. Oh, well, I got the answer the first time. I guess that should have been enough. So usually I would be a perfectionist and I would make sure that I got it all right. But just as this is just for those people that are watching the video, like I was telling Jose right before I turned on the video, right now I have 5 broken ribs and I don't feel like being a perfectionist. So I'll just go with my first answer. Okay, then for part B. So you could say the derivative of natural log, that's going to be 1 divided by whatever's in the parentheses. And then by the chain rule, take the derivative of what's in the parentheses. So the derivative of secant is secant times tangent. And then that's it. All you got to do is cancel out these secants. And then that's just going to be tangent of x. That one was simpler than I thought. Okay, then on to one that will take more work, part C. So for this, we have to use implicit differentiation. Start on the left side, and right here, we need to use the product rule. So the derivative of x squared is 2x, and then leave the e to the y alone, and then plus, leave x squared alone, and now take the derivative of e to the y, which is e to the y, and then by the chain rule, it's times y prime. So that's the first one. Then move over to this one and also do the product rule. So the derivative of y squared is going to be 2y, and then by the chain rule, times y prime. And leave the e function alone. Plus, now leave y squared alone, and take the derivative of e to the x, which is e to the x. And then finally on the right side, it's just going to be derivative of 2x is 2. The next thing is to solve for y prime, look at all those terms that have y prime and leave them on the left side. Not only do you leave them on the left side, but you factor out the y prime from those 2 blue ones. So that'll leave x squared e to the y plus 2y e to the x. And then these red terms that don't have a y prime, then those, you move them to the other side. So subtract them. So the right side will have 2 minus 2x e to the y, and also minus y squared e to the x. And then the last step is just divide both sides by this yellow part. So the right side, the top will stay the same. And then divide both sides by the yellow part. And then the last thing to do is just look at all the terms and see if there's anything that could cancel. And I don't think anything's going to cancel because this term only has a 2. So the only thing that it could cancel is a 2. But this term doesn't have a 2 and this term doesn't have a 2. So nothing could be canceled. So that one's already done. So then just circle that. Jose, do you have any questions?
No.
Then for part D, take the derivative of sine inverse of 1 over x. Each week I space these out more and more, thinking that's definitely going to be enough space. It's never enough space. Okay, so if it was just y equals sine inverse of x, then the derivative is 1 over the square root of 1 minus x squared. So that means whatever's right here in the problem, it has to be right there in the answer. So for this problem, it's going to be a 1 over x that goes in that little green blob. So y prime will equal 1 over the square root of 1 minus, and then in place of x, we now have 1 over x being squared. And then do the chain rule. So take the derivative of 1 over x, and that's the one that we use all the time. So I just remember its derivative is negative 1 over x squared. And then this is definitely a compound or a complex fraction, so it needs to be simplified. Well, for the numerator, it's got 1 times negative 1. So that's just negative 1 for the numerator. And then on the bottom, it has this x squared, and then also it has this square root. So I'll just put the x squared in front. And then for the square root, inside the square root is going to be 1 minus 1 over x squared. And then that is still a compound fraction, so I get to continue with the algebra. So first, I'm going to take this 1 and rewrite it as x squared over x squared. So 1 is the same as x squared over x squared. And then that means that inside the radical, there's one fraction that has x squared minus 1 all over the common denominator x squared. And then we're almost done. So y prime equals negative and 1 on the top. And then for the square root, you could take the square root of the top, which can't be simplified. It's just x squared minus 1. And then take the square root of the bottom, which the square root of x squared is just going to be an x. And then finally, there's only one more step. So this x will cancel one of these x's. So instead of x squared, there's an x on the outside. And then that one's done. That one looks familiar, that answer. So it's got an x on the outside and then square root of x squared minus 1. No. It's actually that one. So actually we were taking the derivative of cosecant inverse, because that's the answer that we got. So we had sine inverse of 1 over x and take the derivative, and we got the same answer. So it turns out that cosecant inverse is the same thing as sine inverse of 1 over x. So if I would have realized that from the beginning, I could have just used that identity and then saved myself some time. But I didn't, so I got to do it the long way. All right, then a quick review of antiderivatives. So the first one is a quotient, and we don't have a quotient rule for antiderivatives. So then I do need to use algebra on this one and break it into two fractions that have the common denominator x to the fourth. The first one will be 2x. The second one will be plus 1. And then on the first one, well, it's x to the 1 over x to the 4, so you subtract their exponents. So the top minus the bottom is going to leave 1 minus 4, or x to the negative 3. And then I could rewrite this other one as x to the negative 4. And then do the opposite of the power rule. So add 1 to the exponent. On this one, that's going to be a negative 2. And then divide by negative 2. On the next one, add 1, so that's going to be negative 3, and then divide by negative 3. So what does it leave? It leaves, well, the 2's will cancel right here, so it's going to leave negative, and then x to the negative 2, and then that one's done. And then this one is going to be negative x to the negative 3 over negative, oh wait, I already put the negative, so just over 3. And if I stopped right now, then Jose, what are the 2 mistakes that I made? Or 2 things that I still have to do? Remember, for antiderivatives at the end, you always have to put
The dx, or the plus c, sorry.
the plus c. So that's one thing that I forgot about. And the other is, well, at least for me personally, I don't like to deal with negative exponents. So I would get rid of the negative exponents. And then the plus c. Okay, so that one's done.
I have a question.
Yes.
I thought you had to use, so on C and D, you use the symbol of the antiderivative.
Yes.
So does it matter if you use y prime for the first A and B?
No, that was part of the point right there, is I wrote 2 of them with the y prime and then find the antiderivative. Okay. Or on C and D, I don't really have to say the word find the antiderivative. It's sort of repetitive because this symbol is really replacing the word find the antiderivative. Then on to B. So for B, it has something inside of a radical. So I should use U substitution and let the U be whatever's inside the radical. So let U equal the inside part. And then the derivative of that's just going to be a 2. And then it would start as du dx, but then multiply both sides by dx. So This one is the same as saying integrate the square root of 2x plus 1 times dx. So you could write it either way. And then this one has a dx and this one has a dx, but it doesn't have the extra 2. So multiply both sides by a half. So if I use this symbol, it's going to be integral, and then you could factor out the 1/2. Next, use the U substitution, so it's going to be the square root of U, and then du. Or another way to write that is integrate U to the 1/2 du. So then add 1 to the exponent, which is 1.5 or 3/2, and divide by 3/2. So let's see, there was already a 1/2. If you're dividing by 3/2, that's the same thing as multiplying by the reciprocal 2/3. And then it's going to have U to the 3/2 and then a plus C. And the last thing is cancel out these 2's. So it's going to leave 1/3. And then replace U with the 2x plus 1. It's raised to the 3/2 and then plus C. Does anybody have questions on that one? So then part A and B were meant to be straightforward. And then C is a little more challenging, and then D is even more challenging. So for C, well, like with the last one, you start with U substitution. Let U be what's inside the radical. So that's just going to be x minus 4. Then take the derivative, and the derivative on the right side is just 1. And then multiply both sides by dx, so it's a 1 dx. And 1 dx is the same thing as dx, so that part is good. X minus 4 inside the radical is going to get replaced with the u. The only problem is we have to know what does x equal. So if you go to this line where I said let u equal x minus 4, well, if you want to know what x equals, then just add 4 to both sides. And so it's u plus 4 that's going to replace the x. So it'll be integral of, replace the x with u plus 4. And then it's going to be radical u. And then du. So then this one is a product. And in Math 3A, we don't have a product rule. There is something like a product rule in Math 3B, but in Math 3A, we can't do it that way yet. So instead, we have to do algebra. So first, with the square root of u, I would just rewrite it as u to the 1/2, and then distribute. So a u times to a u to the 1/2 means the exponent is going to be 1 plus a 1/2, or that's 3/2. And then distribute it to the 4. So it's going to be 4 times u to the 1/2 du. And then it's time to add 1 to the exponent and divide by that number. So 3/2 plus 1 is 5/2, so divide by 5/2. And on the next one, a 1/2 plus 1 is 3/2, so divide by 3/2. So then I don't need the integral symbol anymore. I already did the antiderivative, but I do need to invert the 5/2, so that's going to be 2/5, and then u to the 5/2. Also invert the 3/2, so that'll be 2/3. Ooh, I almost forgot the 4. There's also a 4 right there. And then u to the 3/2, and then put the plus c. And then we're practically done. All I need to do is replace the u with x minus 4. So 2/5, and then x minus 4 is to the 5/2. And then plus, let's see, the next fraction is going to be 8/3. And then u minus, oops, I meant to say x. And then x minus 4 to the 3/2. And then plus c. So then one more integral. Integrate x squared over 1 plus x squared. So first, try U substitution, and you should let U equal the bottom part. And then the derivative of that is going to be 2x dx. And then the problem with that is this says x dx, but this says x squared dx. So Jose, don't even write this next part, but you could try and say, well, x squared could be factored as an x times an x. And then this x dx, well, that is what this says. So it's going to get replaced with 1/2 du. And the bottom is going to get replaced with u. But then like in the last problem, we have this extra x. So then you could try and go like I did last time, go right here and solve for x. And that would be u minus 1 equals x squared. And then take the square root. So it seems like it's going to work out. But then when you replace this red x with the square root of u minus 1, and then you have to replace the x dx, which is in purple right here. So you need to multiply both sides by 1/2. So that would be 1/2 du. And then the bottom part gets replaced with u. And then that integral right there, well, again, we don't have a quotient rule for integrals. And I could try another U substitution, but it's basically just going to turn back into the other problem that we just started with. And we can't do anything like, oh, on the top, why don't you write it as square root of u minus square root of 1? Well, you can't do that with square roots. So this U substitution did not work out. Good thing I've got an eraser. Okay, so what else could we do? And here's the reason that I picked that problem, to show you something that is not very often used, but every once in a while, it turns out to be useful. So I'm really going to end up like I did on this one and break it into 2 fractions with a common denominator. So with the problem that I have, there's 2 ways to look at it. One is, instead of x squared, if it just had a 1, I could be done in one step because the answer to that is tangent inverse. So that's one thing to think of. The other thing to think of, well, it does have an x squared. But what if it had a 1 plus x squared? So if it had a 1 plus x squared on the top and a 1 plus x squared on the bottom, that just simplifies to be a 1. And a 1 is very easy to integrate. The answer is just x. So here's the little trick that you don't often have to do, but it's nice every once in a while because it could save you a lot of work. And that is, okay, right there in red, I added in a 1. So what I'll do on the other side is I'll balance it by subtracting 1. So the red positive 1 and the red negative 1, technically they cancel each other out. But then, like I did on this problem, part A, separate this into two fractions. One of them is going to have this as its numerator, and the other one's going to have this as its numerator. So you have to keep the denominators the same, 1 plus x squared. And then the first one will have that purple part, so that's going to be 1 plus x squared. And then the other one will have minus 1. So the first one, because it's 1 plus x squared divided by itself, that's just a 1. And then just copy down the minus 1 over 1 plus x squared. And then we only have one last step. And that is the antiderivative of 1 is just an x minus the antiderivative of 1 over 1 plus x squared. That's tangent inverse of x. And then put a plus c, and it's done. So like I said, this idea, it's not used very often, but every once in a while, it's good to have that idea in the back of your head. Then on to stuff that is much more recent, not really, well, I guess it's sort of review for my class, but more recent. Find the area between sine from 0 to pi. So there's the sine function. And then also the line y equals x minus 1. So I would need to go down on the x-axis or the y-axis by 1 and then make a line that's got a slope of 1. So find the area between them. Well, for one thing, notice that they intersect right here. So we're going to have to find that intersection point right there. And then once we do that, we could integrate to find this orange area. And for that orange area, the sine function is on the top and the x minus 1 function is on the bottom, which is important because when you're finding area, you have to do the top function minus the bottom function. And then for the other area between them, going up to pi, so that would be this area right here. And then in that case, it's going to be the the line x minus 1 is on top, and then it's actually the sine function that's on the bottom. So in order to find the total area, first for the orange area, it has to be the top function, so that's sine of x, minus the bottom function, and the limits of integration are going to go from 0 until I get to this green question mark. So from 0 to the question mark. Then plus for the blue area, you then have to have the top function, which is x minus 1, minus the bottom function, which is sine. And then that's going to go from the question mark until pi. Now, before I can do all that integrating, I still need to find out where's that green question mark. So in other words, where does sine of x equal x minus 1? And then that is a good time to use Newton's method. So this one has a combination of section 6.1, at least in the book that we use, section 6.1, find the area between two curves. And then back in chapter 5 when we did Newton's method. So I don't have enough space. So I'm going to need to take this one and move to where I have some more space. What about at the very bottom? Yeah. Okay, so for Newton's method, the first thing to do is you set it equal to 0. So I'll just subtract the x and add the 1. So it's going to be sine of x and minus x and plus 1. And then you call that the function f of x. So sine of x minus x plus 1. And then you take the derivative. The derivative of sine is cosine, and then minus 1. And then the formula for Newton's method is it's x minus the function over the derivative. And then I need a guess. Well, let me see on that graph. This is 3.14, etc. So I would guess that the question mark is at about 2.5. I'll just guess 2.5. And then use the calculator. So first take 2.5 and then store that as x. And then the formula is x minus sine of x. And then it was minus x plus 1. And then divided by the derivative, so that's cosine of x. And then the derivative of minus x would be minus 1. And it says the answer is closer to 1.99. And then store that as x. And then do the formula again. Now it's 1936, right before World War II. And then 1935, I think we almost got it. And then store that as X. And do it one more time. All right, there it is, 1935. So that's where the green question mark is. Okay, then go back to the integration that we were doing and replace the question mark with 1935. So 1.935. So on this first one, the antiderivative of sine is negative cosine. And the antiderivative of this negative x will be negative x squared over 2. And then this last number is a +1, so that'll be plus x. Evaluated from 0 to 1.935. Plus, and then the antiderivative of this x will be x squared over 2. Then there's a -1, so the antiderivative is minus x. And then the antiderivative for negative sine is positive cosine. And then evaluate that from 1.935 to pi. Let me see. It's 11:45. And I still have 2 full problems to do. So I think I'm going to skip typing all those decimals into the calculator. That's going to take me a while. So I'm going to skip and go to number 4. So consider the region between the x-axis and this upside down parabola in quadrant 1. So x squared minus 4x. Y equals x squared minus 4x. Whoops, not chemistry. 4x. I forgot a negative sign. So that was supposed to be a negative in front. No. Did I type it in wrong? X squared minus 4x. Oh, yeah, I forgot the negative. So I wanted a negative in front of it. Insert a negative parentheses. Yeah, because I wanted the graph to look like that. So it crosses the x-axis at 0, and at 4. At 0 and 4. Okay, so once I have that negative there, then it goes like this. 0 and 4. And then find this area. So that means it's integral from 0 to 4. And then all I have to do is integrate the function. So integrate negative of x squared minus 4x. And then I think I'm going to go ahead and distribute the negative first, or at least factor out the negative. I'll factor out the negative. So that'll be negative, and then x cubed over 3 for the first one. And then for the 4x, well, right now its exponent is a 1, and if you add 1, that'll be 2, and then divide by 2. So that's going to leave negative 2x squared. And then evaluate that from 0 to 4. So 4 to the third over 3 minus 2, and then 4 gets squared. And then minus, well, when you plug a 0 in for x, both of those are actually going to be 0. So that's just going to be minus a 0. So how much is that? So I guess I could distribute the negative. Negative 4 to the third over 3. And then if I distribute the negative over here, it's going to be positive. And what's that? 16 times 2? So that'll be 32 is positive, and then minus 64 thirds. 32 minus 64 thirds. 32 minus 64 thirds is 10 and 2/3. Or 10.667 if you go to 3 decimals. So then let's see if I got it right. Go back to the graph. And then ask the calculator, integrate from 0 to 4. And sure enough, it says that the area is 10.667. So I got that one right. And I think I'm going to skip B. So let's say, have you done the homework that's due on Friday?
No.
Nope, I didn't think so. And then those people that are in Miss Contreras's class, if you're watching this, well, you guys aren't even going to do those. And then my class isn't doing that till Friday. So I think I was getting a little ambitious by throwing that one in there. I should do that one next week. Then for the last part, find the horizontal asymptote. So if you have a graph and it does whatever, but then it eventually levels off, that's a horizontal asymptote. And for this, x is going off to the right forever. So in other words, x is going to infinity. So another way I could say find the horizontal asymptote is, what's the limit as x goes to infinity if it's natural log of 1 over x over x? Well, if you look at this 1 over x part, 1 over something really big like infinity is so small that it's going to 0. So the top part is basically saying what's natural log of 0. The natural log function looks like this. And if x is really close to 0, then this function is going down to negative infinity. So the top part is going to negative infinity. And then the x on the bottom, that's going to infinity. And then that's one of the rules for using L'Hopital's rule, that you have to have either 0 divided by 0 or infinity divided by infinity. So since we have infinity divided by infinity, then we could use L'Hopital's rule. So by L'Hopital's rule, all you need to do is take the derivative on the top and take the derivative on the bottom. Well, the derivative on the bottom is easy. That's just a 1. The derivative on the top, well, the derivative for natural log is 1 divided by whatever's in the parentheses. So that's going to be 1 divided by 1 over x. And then for that derivative on the top, you also have to do the chain rule. So the derivative of 1 over x, that's negative 1 over x squared. And then simplify that. Well, when you have 1 divided by something, that means invert the denominators. That means it's going to become an x over 1 that's getting multiplied with negative 1 over x squared. And then I could even cancel and have this x cancel one of these x's. So all that's left is negative 1 over x. And then that is basically 1 divided by infinity, which is 0. And it is going to be negative, but basically it's going to be negative, smaller and smaller and smaller numbers until it becomes so small it's 0. And negative 0 is the same thing as 0, so it should equal 0. Now to see if I got it right. So graph the original function. The natural log of 1 over x gets divided by x. So y equals the natural log of 1 divided by x gets divided by x. And then look at the graph and then follow it to the right a long ways. And then you could see, like right there, it's a y equals a negative 0.016. And if you keep going, it is negative, but it's getting smaller and smaller and smaller. There we go. Until right there, it's a negative 0.01. So it's eventually going to become a 0. So it looks like I got that one right. And then for the last one. I got 5 minutes.
There's a number 6.
Dang. I must have made this up before I crashed my mountain bike. And I was feeling really ambitious. Well, let's do part B. So again, it's saying find the limit as x goes to infinity. And then this one is 1 over x to the x. Then I was thinking it would be nice to use L'Hopital's rule. But the thing is, L'Hopital's rule is when you have one function divided by a second function. And I do have one function divided by a second function, but then it's raised to an x. So there's a long way and a short way. I'm not going to do the whole long way, but the long way would go like this. You go, well, we're talking about the function, and I'm just going to simplify and say y equals 1 over x is raised to the x. And then what I'm going to do is take a natural log of both sides. And I'm not even doing calculus right now. I'm just doing pre-calculus. And then the reason that I did that is because now this x, you could bring it down here and multiply. That's a rule from logarithms. And then you go, well, that didn't really help, because if we're going to use L'Hopital's rule, it's supposed to be one function divided by the other function. And this right here is the main reason that I picked this one, is because I could actually make that on the right side. I could make that one function divided by the other function. So the one function would be the natural log function. And then I'm going to get fancy with this x. And I'm going to say that is the same thing as if you divide by 1 over x. So we usually you would take something that's more complicated, like dividing by 1 over x, and then you would need to simplify it. But sometimes you go the other way around. Now on the left side, it still says natural log of y. So now find the limit as x goes to infinity for ln 1 over x over 1 over x. And then here's the other reason that I want to do this problem, is because this has 1 over x. Oh, that doesn't show up very well. So this has 1 over x and this has 1 over x. They're the same thing. So then I could even use U substitution, not for integrals, but just let U equal 1 over x. So that simplifies it, because then it's going to be natural log of U over U. Now, if x is going to infinity, this is going to become 1 over infinity, and that goes to 0. So that means it's going to be the limit as U goes to 0. Okay, it's already 12 o'clock. That's the long way to do it. I didn't even finish. And that was already, but I did want to show you those few important steps. But there's a different way to do it. And that is, go back to the original problem. And if you have a fraction that's raised to a power x, that means the top, which is a 1, it's raised to x. And the bottom is raised to x. And then this part means you have 1 times 1 times 1 times 1 times 1. You just have a bunch of 1s. So if you multiply 1 by itself a whole bunch of times, that means it still equals 1. And then the top is still x to the x. So basically it's 1 divided by infinity raised to the infinity. So infinity raised to infinity, that is so big that it's infinity. So we basically have 1 divided by infinity, so the answer is 0. So that's the faster way to do it. Eventually we would have gotten the same thing with the other way, but that's the long way. And then let me check and see if that's right. So graph the original problem and follow it out to the right. So it is y equals, it was 1 divided by x. 1 divided by x is raised to the, my fat fingers, I have to use my pen. So then when you graph that one and then follow it off to the right, so already I'm over here in the like 3,000s and it says the answer is 0. So this function, it's so tiny, the calculator thinks it equals 0 this whole time. So sure enough, the answer was supposed to be 0. So what do you think, Jose? It's 12:03. Shall we call it a day or shall we try to power through number 6?
I'm gonna have to go right now. I have
Okay.
something to do right now. Do we turn in the AEW how it is, unfinished, incomplete, or
No, just the work that I did. So like when I do the one on Thursday, I would delete that one. And then as far as that one with the integral with those, so you could stop right there. So just the ones that I did, that's what you need to turn in.
okay?
All right.
All right. Thank you.
All right. Have a good day.
Yeah, you too.
Bye.